Okay, so today we're gonna talk about the special senses a little bit more. How was that quiz? Was that more doable?
Yeah, a little bit better.
I see, I listened. I made this afterward, after you told me that the brain was pretty hard. Or the spinal cord was even harder. So in this chapter we'll discuss the sensory nervous system in more detail. We'll spend most of our time covering the special senses, but we'll start with some general concepts. One of them is the fact that we differentiate between awareness of a sense that is delivered to the brain and having it be interpreted for meaning. This is actually often discussed in modern psychology when we try to understand suffering. There's a significant portion of our suffering that comes from the interpretation of a stimulus such as pain and not simply the awareness. We talked about that. That's when you twist your ankle and you beat yourself out versus it's like, oh, stuff happens, too bad. Or when you study, it's like, oh, I really hate this topic. I'm really so over it. I don't even want to start studying. You suffer so much before you even start studying. That's the second mountain of studying. We don't need that second mountain of studying. So it's all that stuff, but it has to do with interpretation of a stimulus versus just simply perception. What is the terminology used to describe the two? Perception and interpretation, right? Good. Sensory receptors are found throughout the body. They inform the brain of different types of stimuli. Choose all that apply.
You said sensation. That was sensation and first.
Wait, what?
Sensation.
Oh, not inspiration. Never mind. Sensation. Yeah. Perception and sensation. Yeah, sometimes it takes me a long time to come up with the worst answers. And then here, choose all that apply. Which one apply? All of them, right? Good. Don't you like that picture? I love when they trick me. So that the old man and the flutist is the child. So sensation is that awareness of change. So what we see in that perception is our interpretation of it. And then here we got a bunch of the sensors for us. So we sense for pain. Nociception is pain. Meissner's is touch, and then we have pressure, posilions, and then we have thermoreceptors, and then we got the special senses. And the special senses are discussed most in detail. The sensors, the receptors, they either are superficial right in the skin or deeper in muscle and tendons, or they're also in internal organs. And then, of course, we have the ones in the eyeball, the ear, the tongue, and the nose. And I think that's number 3, right? What are complex receptors? What do complex receptors transduce? Pain? Question mark? No? Yes? Yeah, everybody has a hard time with that one. So, you look at the special senses are the ones that are difficult and very complex. The simple senses like pain and temperature and touch, they are very simple. They either are free nerve endings that get cut, like a pain. If you cut yourself and it hurts, that's simple. A nerve that got cut, and then it gets irritated because it got cut, and so it sends a signal to the brain. That's very simple. Or ones that are layered like onions. They have an inside and they have shells around it, and when we compress the skin a little bit, those layers come together and then they transduce an electrical impulse. Those are also quite simple from our perspective. So the complex ones are ones we use to detect odors in the nose, or taste in the tongue, or hear, or balance, and also vision, sight. Those are very difficult, and we spend a little time discussing those. So the answer here
He's telling me that.
I was looking for would be, anybody? Come on, take
I
a
got
list.
partial, so.
What do you think? Vision? Huh?
All but touch
There,
and pain.
there you go. All of them but touch and pain.
Yeah.
I know that was difficult. With those multiples, I'm still trying to figure out if the computer makes a mistake or not. So feel free to text me if you have question marks. Do not get yourself crazy over it. I know, easy to say, right? Many nerve stimuli don't need to excite our brain at all times. It often is more important to register a change and not continuously be made aware of a specific temperature, for example. Often when we take a shower, at the beginning of the shower it's cooler, and then at the end we get used to it, so we want it more, so we make it warmer and warmer. But then you get back in the shower the next morning, it's like, damn, it's hot. I know, right? I think we all are so simple people. Other senses, such as touch adapts, like you put on a sock, first you feel it, and then it's a nice fuzzy sock, it's just a nice fuzzy sock, and it's like not registered anymore. The same is with pressure, that's kind of the sock department. Also, the brightness of light can also adapt. Can you give me two receptor types that do not adapt?
Nociceptor and
Receptors.
Those two, huh?
Oh, yeah.
Yeah. What are nociceptors? What do they code for? Pain, right? So they code for pain, and noci means danger, actually. So that's where this is actually right where we understand the importance of pain and what pain is. Pain is here to tell us that there's something that's dangerous. Something needs to be done about something. And so that's because that's very important, because very often we want to just get rid of the pain. And that is okay, but it is not necessarily its purpose, and so it can be counterproductive. So we want to be aware of that. Acuteness, that's fine. Chronic pain, you know, just taking a pain pill for chronic pain, that's not going to do it very often. We get rid of chronic pain by motion and strengthening stuff. But anyway, that's back to my other topic. So those two do not adapt. Pain and proprioceptor. And proprioceptors are the ones that tell your brain where your body's in space. So a lot of those you find in tendons. So the fact you can close your eyes and still do that, that's proprioceptors, that it doesn't go all over the place. Because how the heck you know when you close your eyes that you can still find your nose with a finger? That's because all these muscles and joints and all that stuff has sensors in it that continuously feed the brain where everything is in space. If we do not want to have those adapt, right? If you don't have like a good example, if you don't have nociceptors, if you have nociceptors adapting, is somebody doesn't feel pain, they walk on the side of a foot. They don't feel the pain, they destroy their foot immediately. You want that feedback, otherwise you're messed up. This is, huh? Yeah, right. Well, yeah. Who doesn't twist an ankle, right? But keep
It was
twisting.
broken, I was walking on it.
We might have to talk. But another thing that, this is of course the good one we can do, right? Is you hold one hand in the cold water, one in the hot water. The one from the hot to the lukewarm feels cold, the other one feels warm. So that's that temperature adaptation. The other one that's interesting that I bring here is pain doesn't adapt as a input. Proprioception also doesn't adapt. Proprioception is elicited, for example, when you rub something. Like if a kid runs in a wall with the forehead, you rub the forehead and say it's okay, so the kid doesn't cry. Well, you do neurologically, you activate what's called the gate theory. So the pain goes in as long as the kid runs with the head into the wall and realizes, oh my God, this is hurting in here because it banged it. But as soon as we rub it, as soon as we increase the proprioceptive stimulus, that door gets shut and the pain can no longer go into the brain. That's why with a lot of our pains, movement helps. Like significantly. And if it doesn't, then stop moving. But if it does, give it a shot. And and that's the theory behind it. You know, I realize I have to teach this because I talk to some MDs. A lot of MDs are not aware of this theory. But that was from the 50s, and that's one of the fundamentals why massage works, why movement stuff works, why chiropractic works, all that stuff. So anyway, it's good to know. This is to try to get everybody from the couch potato life away, class. When we discussed the primary sensory cortex in the brain, we mentioned that the distribution of nerve receptors is not equal for all body areas. For example, the lips and fingertips are much more densely innervated with sensory nerve receptors than the back. We can feel a coin in our pocket and know what size it is. Try doing that with the back. How big an area is that one receptor innervate is called a receptive field. What test can be used to determine the size of a receptive field?
2-point discrimination.
2-point discrimination test.
I did, and I got it wrong.
You got it wrong?
I said test on the end.
Can I see my computer real quick?
I put 2-point determination wrong. I did 2.
They all got arguing today.
Because I did it, I was wrong, and then when I added test, I got it right. Hey, what the hell? No, I didn't add test.
You didn't add test?
No.
Huh?
I said, what test is it? It's the 2-point determination.
Okay, I can see that.
I was saying, like, how is this?
And if you get it wrong, you didn't think of putting test behind it?
No.
Okay.
I just said, I accept that being wrong.
Huh?
I accepted being wrong.
Yeah.
Well, so generally speaking, you will not go wrong if you spell it the way it's in the book.
I did. I put 2.
Even with test?
I did the same thing.
You put test.
I put 2-point determination. It was all wrong.
Yeah, because I thought you were going to put test behind it.
Well, I guess you gotta put test behind it in order to get it right.
Yeah, but if you put test behind it, I think you're going right. Hold on. What number is that?
And then 5. 5.
No, we're only at 5.
Unfortunately.
Yeah, I got test on every one of them. Oh well. I expect the test will come in. Believe me, it's hard to figure out what people are writing. Well,
There's no point in fighting.
no, but next time you just look in the book and then you do it exactly how it's in the book. No, you didn't say test.
Because you asked what test it is in. You didn't say that you put test on behind it. I told you what test it is.
Okay, I hear you. All right. Well, I want a test.
I see.
And try. Well, because at the end it's a procedure, so that is a test. So that, technically speaking. I should just say, what procedure? Maybe I'll put the question on it. In trying to understand vision, we have to mostly study the eyeball. Now we get there. The eyeball is a sphere that transforms the visual world we see into nerve impulses, which is electricity. And that's the language of the brain can understand. So in the eyeball, we have a light that comes in on one end and a cable leaves the other end. Inside, a clear picture of what we see has to project onto a tiny screen in the back of the eyeball. There, a gazillion, and it's really a lot of them, maybe not a gazillion, but a lot of them, receptors get activated when projected on. They then send a signal to the brain where it appears as a pixel projected onto the primary visual cortex of the occipital lobe. So it's in the back. So the lobe in the back is the visual lobe. Sort of basically they're recreating the visual image. Let's now consider the parts of the incredible organ. Can you match the function of the different layers of the eyeball? The tunics. What's the fibrous tunic? The outside, huh? So that's the hard stuff. That's the, when we look at an eyeball, now might be a good time to get an eyeball, but when we look at an eyeball, the white stuff is the sclera, The front stuff that's clear is the cornea. All right, the vascular tunic. Which one?
Iris.
The iris, right? So that's the front part. Here's the iris. The colory part is the iris. And the ciliary body is the muscle that's gonna determine how big the iris is, or how big the pupil is, basically, because the pupil is the hole in the iris. And we'll look at that in a minute. And then, we lost the lens. We lost the lens. And then the inside layer is the retina. And what's that? That's the pigment, and that's where we pick up the nerve, the light, and then the light gets transduced into nerve. That's right there. That's why it says the neural layer. See, that's a nice eyeball. I know. There we go. Yes?
As you're explaining this stuff, can you explain how you get cataracts and what's it look like when it's bad?
We get a little bit into that, yeah. In a few slides. Huh?
Okay.
Yeah, in a few slides.
Okay.
Moving right along here. If you look at the cross section of the eyeball, we can separate an area behind and one in front of the lens or the iris. The larger space behind the lens, known as the posterior chamber, consists of a yellow-like, somewhat firm but wobbly substance called the vitreous humor. It helps the eyeball's structural integrity by pressing outward against its walls. In the front chamber, a more liquid aqueous humor, so aqueous means watery, provides internal pressure and also brings nutrients to the eyeball. Nutrients get used up, so this fluid has to be secreted from the bloodstream and then drained in order to not accumulate and exert excessive pressure onto the eyeball. What is the place where the aqueous humor drains from? Canal of Schlemm. That's right. I thought its name is so cool, right? If the canal of Schlemm, talk about the first pathology here, if the canal of Schlemm doesn't drain, we get glaucoma. That's one of them. So if that canal does not drain properly, the liquid stays behind, that pushes more pressure onto the eyeball, we get glaucoma. That's what that is. So there's one thing, that's a problem. And then all of a sudden in the Bay Area, everybody has glaucoma.
Yeah, my sister's ready to have surgery.
No, they all want pot.
Next
Yeah, but
month.
they also all want pot. You remember when there was the pot licenses? Every doctor would write that the patient has glaucoma, so they get marijuana license.
Yep.
You didn't know that. You were really been living. But yeah, it is very common too, of course. The eye sees a picture best when projected to a specific area onto the retina that is most densely populated with receptors. In order to do that, the eyeball has to be able to move freely around on its own axis. It does that by having 6 muscles attached onto it and pull it in all possible directions. The 4 recti muscles enable us to look up, down, and to the sides. What muscle pulls the eyeball up and out? Inferior, what? Inferior oblique. My muscle pet peeve. So, well, these are cool, you know, we got these 4s, all right? The 4 are right, they're going straight from the eyeball, from the back to the front. So they're called rectus muscles, the recti. We have one on top, superior, one on the middle, medial, one on the underside, inferior, and one on the lateral side, lateral. Now, how the heck you know this is lateral and this is medial?
Yeah.
Yeah, right.
No.
Here. That little thing out here on the right top is when things don't go so well and you cry. That's the lacrimal gland. That's the tear gland.
So this is
So tears come from the outside of the eyeball and go across. Huh? And go across to the inside, and then we need a tissue. Because they drain through the nose.
So medial's out.
So medial is away from the, no, medial is away from the lacrimal gland, on the eyeball because the lacrimal gland is on the outside. Well, you have to orient yourself. What's medial, what's lateral, right?
So medial is.
So
Medial is on the side of the.
So yeah, lateral is where the gland is.
Okay, so lateral is gland.
Medial is the opposite.
Medial is the opposite.
Right.
Medial is inside.
Mm-hmm. It's important to know that the gland's on the outside because the tears drain this way. So if you want to flush something out of the tear, you got a sand core in there or something, and you get watery eyes. You don't want to rub it like this away from where it drains out. You want to rub it with the drainage. Did your mother tell you that? Oh, I learned that from my mom.
This one.
Hello, Mom. Go inward. Drain the crap out that goes into the eyeball. So that's 4 muscles. Now we have 2 more, the obliques. That was the answer. So you have an inferior oblique and a superior oblique. The superior oblique on the eyeball is this white thing on top here. That weird thing, opposite of the gland. So that's actually a tendon. So that tendon comes out, and then the nose is right here. See, the nose is right here. So that thing comes out, goes forward, and has a pulley on the nose side, on the medial side, and then reaches back to where everybody else is. So that's the muscle goes like in this weird shape and has a little ring. See, you can see.
What's the name of that muscle?
Huh?
What's the name of that muscle?
That muscle is called the superior oblique muscle.
So this white thing right here?
That white thing right here.
This next to
So if you see that pulls, and there's a pulley, so when you yank on it, it pulls this way. So it pulls out and down. So the superior oblique pulls out and down, which is kind of down and up. Superior is not down, that's an up, right? So you have the opposite of the action to the neck. That's why I put it in the quiz, so you think about it. And then the inferior oblique is on the other side here, going up and down on the eyeball. And when that pulls, it pulls the eye up and out.
here.
This one right here?
That one right
The
here.
little bottom red.
The one going out. The recti go back.
Oh.
That one going up and down is the oblique. And so that oblique, when that yanks on, it goes up and out. Look. Super oblique, inferior oblique.
And this is the lateral gland.
And the gland on the outside is the lacrimal gland. I know, we're getting better at Trivial Pursuit. Now, let's better understand the transformation from a light stimulus into a nerve impulse. The whole process boils down to molecules stacked up in round discs changing shape, then activated by light waves. There are 2 types of photoreceptor. One of them is so sensitive that it picks up dim light. Those get overwhelmed when the light is too bright and they stop firing. We feel the process of them bleaching out when we go from a dark spot to a bright light quickly. The other receptor type is activated when it is light. They come in 3 different subtypes that help us see color. What's that type called? The cones. So this stuff is pretty darn freaking cool. So you gotta have light come in. The whole eyeball is all this, and then it projects the light to the back of the eyeball.
Which one is the eyeball, Dr. M? The 2, the 10, what?
No, well,
What's the eyeball?
no, the eyeball is the whole thing. So the eyeball is this whole thing.
Pupil.
Yeah, that's the pupil is the hole in the middle. So the light comes in from here through the pupil, that's right, gets projected into the back of the eyeball, and that here gets picked up, and then that's the retina. That's where we have those rods and those cones. And the rods pick up dim light. So when you go outside after school, you have light around, but still it's darker, so it's going to take you a moment to get used to that darkness. And then when you go back into a light, like coming into a bright light, it almost burns. And when it burns, you overwhelm the rods and fire so much light at them that they completely fire for a hot second, and then they're used up and they can't fire anymore. They're bleached out. Because the way that we see in the eye is that we have these stacked up discs, and we have a molecule inside them change shape when it gets light thrown at it. And that's the vision. That's how molecular it gets. I'm not going to go with all this stuff. I don't, you know. But that process is, it's a molecule that changes shape when it gets hit with a light.
It straightens out.
Yeah. And so the rods, their molecules, when we go in bright light, they get completely all just changed. So they're all just fire, and then they're overwhelmed, and they have to regenerate to then refire. And so as we go from bright light then to a light source, to darkness, those slowly have to regenerate. And so slowly, over 20 minutes, we start seeing better and better in dark. And the cones are here for light, for light vision, for color vision. And they don't even fire when we go to the dark. They just fire when we are in a light source. They don't even have, the light is not strong enough to make them do anything in a darkness. And so that's the two different kinds. So the rods are here for night vision, and the cones are here for color vision or light / day vision. I know, Meryl, you had a question?
Is retina supposed to be on our list?
No. See, the light comes in here, and then the picture gets projected back here, and that's where the rods and the cones are, and they change the molecule, and then we see it. Kind of like that. It's a little more complicated, but that's a pretty good start. There is a part now, peripheral vision, that projects onto the retina where the optic nerve leaves the eyeball. That area is called the optic disc and has no photoreceptors and cannot transduce a picture. The brain actually just imagines that part of the visual field. On the other hand, the area of the retina coding for the center of a visual field is most densely filled with receptors, giving us the best, most acute vision. What's that area called? Fovea Centralis. Did it take that one?
I just forgot my number wrong.
Oh. So, the optic disc is where the eyeball leaves. So that's called a blind spot. So there's no receptors back here. You got to use that space for the nerves to get out. And so that's one side. That's the optic disc. That's right here. You can see that when you look at the eye, you can see where all the vessels come in or go out. So where the vessels converge, that's the nerve right there. And then you've got this other area that's a little lighter, like here. It's not as easy to pick up. And that's the macula lutea, the outer portion, and on the inside where it's darkest, that's the fovea centralis. And in that area, you can see here the slide. No,
Is this number 10?
probably.
Yeah, it's 10.
You can see here on the slide where it goes down, and what that means, where it goes down, what that means is that these nerves, these cell receptors that stack up like that, they're all pushed to the side, and you only have the rods and the cones. So the light can come straight directly onto those rods and cones, and do not have to go through other cells that are stacked on top of the rods and the cones. Because when you look at the neurology, you actually have the rods and the cones that transduce the vision into electricity, and then you have a couple of layers of integration cells that make sure that the nerve, this is a gazillion receptors in here. So we're making it simple, somewhat. But what's interesting is if you think about it, like how the world did, we got created that the light comes in and has to first go through cells before it hits the back that then transduces that light. You're losing all this light. And that's why the fovea centralis, all these cells that will lose that light, will be pushed to the side and sort of yanked over that there's a room that has only these cones in it. And that's then this area right here, that's why that goes flat. You see how it flattens out. Does that make sense, somewhat?
Yes.
Good. And that was number 10.
I got that one wrong.
When we need reading glasses as we get older because the lens becomes less flexible, which makes it bend less. Some of us also need glasses because it is very delicate to project the perfect image onto the retina. In some of us, the light rays reunite not quite on it, but either a little in front or a little behind it. In farsightedness, the eyeball is short and the image gets projected behind it. Makes us see close images, objects blurry. Is that true or false?
True.
True. I know, that's all I can remember, that it's true. So that's this picture here, right? Where you just the eyeball shape is not quite, and we have to change the ray as it comes in and bend it a little bit different that we can project the image right onto the retina. So that's farsightedness and nearsightedness. And then let's see if we have a picture of the cataract. We can understand sharpness, acuity of vision. No, then we also have this here, the cataracts. Meryl, that's the cataracts is when we have inside, the lens needs to be transparent so you can see through. But if we get older, the protein needs to use sugar to live, and that sugar that it is used will slowly get clumping, and that's the cataracts. And so then the lens looks more like that, and the picture looks fuzzier like that. So that's, but we're really good with changing these lenses out. So that's the cool part about it. So, I mean, it seems like, how the heck are they going to do that? But apparently they're good at it. So we're not going to argue with good results. And so that's that. And so when we want to look at the sharpness of the vision and want to measure how good do we see, what do we use to do that?
Eye chart.
The eye chart, which one?
Snell.
The Snellen chart. And so we actually have a little part of the lab where I have a Snellen chart, so you can do a little bit of that on each chart. Interestingly, we can see 3D. This is made possible because we have two eyeballs that also pick up the same picture, just from a slightly different perspective or angle. If you overlay those pictures, voila, we can see three-dimensional. It's also just cool to have two eyes. In case one doesn't work, we can still see. In order to be able to overlay information from two different eyes, both stimuli have to be processed in the same area of the primary visual cortex. This is accomplished by having half of the optic nerve cross over to the other side and join that side's optic nerve. Now both impressions of the visual field can be brought to the occipital lobe for processing. Pretty smart. What is that area called where the nerve crosses over? Optic chiasm. Optic chiasm, very short. So that's right here, the optic chiasm. When you look underneath the brain, right above the pituitary gland on your brains, there's the little nerves crossover on the brains that we study. That's the optic chiasm, it's actually on the brain. And so the nerve, the optic nerve goes from the eyeball to the chiasm, and then from there, we project back to the thalamus, and then from the thalamus we go to the primary occipital cortex. So we call it optic nerve, the optic chiasm is here, then it's called optic tract, and after the thalamus, that's the thalamus, that's just a specific area in the thalamus. It's called the optic radiation. But what's really the interesting portion of this 3D portion is kind of over here. So when you look at a visual field, you look at the left and the right visual field. And when you look at who picks up which visual field, you can see that on the right visual field is picked up by the medial half of the right eyeball and the lateral half of the left eyeball, if you see how the vision goes. And so what you want to do in order to overlay those two pictures in the occipital cortex, you want both of those two data points at the same side. And so what the brain does, it takes the medial half of the not the visual field, but the medial half of the retina of that one eyeball and carries over to join the lateral part of the retina of the other eyeball behind the optic chiasm. And that's what the optic chiasm does. And so one of the things where you can make use of that is when you look at pathologies, what happens where when something gets, trashed. So when you have a problem in the optic nerve, you just one eyeball doesn't see. That's just the end of that. Normal 3D. When you got a problem on the optic chiasm, you're gonna get what we call tunnel vision, because only the outside halves of the eyeballs get projected back, and that only visualizes the more medial side of the visual field, not the lateral side. See, but we need 3Ds is right in the middle of the field. The outside is not that important. We can always move the eyeball to it. But this is interesting because you can use, when somebody come in and say, like, I can only see this here, I can't see out here. You can use that data and transduce and say, like, oh, maybe he's got something wrong with the optic chiasm. And in brain, the pituitary gland is right underneath the optic chiasm, and pituitary gland is glandular, that epithelium that grows a lot. That could be a problem. Pituitary tumor could do that. So this is an interesting place where you can see a deficit, a sign on the outside, and you can transduce to the inside or deduce of what it could be, and then you can take a visual and see. You can't open it unless you have to take it away, but that's pretty deep in the brain. That's a problem. And so that's what I wanted to go with. That is that pathway there. All right, so let's see. That's this. You got that? A little bit as understanding? That's a general overview. Tears are great. They clean, nourish our eyes. They also help us process emotionally. Crying stimulates release of endorphins. You hopefully have noticed that before. Otherwise, you better get to it. And don't just suffer needlessly. What's the tear gland called? The lacrimal gland.
How you pronounce it?
Lacrimal gland. Well, see, the cool thing about all these terms is you can basically say what you want. You don't have to be fully accurate. It's just medical terms, that's the pronunciation is what you like. I got to make sure there's also the concepts. Oh, let's do this here. Light rays entering the eye have to bend, refract in a perfect way so that they ruin the retina, not worry. The lens can change shape, which changes the angle of the light that bend. It accommodates images differently at distance. The rounder it is, the steeper the angle it bends the light rays. Remember the concepts. Does a round lens best focus images that are closer or far away? Have you answered that?
Yeah. Petra's portion.
No, I meant Petra's portion. Okay.
I was like, wait, no.
I was reading the concept, but we'll go back to that in a little bit. I'm sorry. I was looking at the lens here. I was having a question in the concepts that was still pertaining to the eyeball, so I wanted to just go through that real quick. Did you do the concepts? Yeah, so the rounder lens, a thicker, rounder lens, more curved, does it accommodate for objects that are closer or farther away?
Yes, I did.
They're closer, right? Yeah? Good. That was right here. I just wanted to make sure you guys got that. Because the next question now goes for the eyebrows, right? We can, yes. So let's do those real quick. Give me 2 reasons for why we have eyebrows. Shade them and keep the sweat out. Keep the sun out, keep the sweat out. I know. I had to put that in, huh? And then what's conjunctivitis? The pink eye, yes, the pink eye. Conjunctivitis is pink eye. So that's when we have a membrane that overlays the eyeball and the eyelid, and that can get inflamed, and that's conjunctivitis. And that's important to know because it's very contagious. This is the one place you keep the kid at home. Well, mine doesn't cough. Well, that doesn't matter. When it's pink eye, you keep him at home. And you stay at home too because you don't want a whole office to get the conjunctivitis. I mean, that's one of those, you just need to do it, unfortunately. And everybody will understand. So those were those two. But then we go to the ear. When we see an ear, we likely associate it with a sense of hearing. We also have a sense of balance and equilibrium in that area. In which part of the skull do we find the inner ear? That was that petrous portion, right? Oh, and I have this picture that I gotta bring, I forgot, to show you a really pretty way of seeing the ear, the inner ear. All right, petrous portion. Our ears pick up sound waves that travel through a funnel-shaped external visible ear. They then vibrate the eardrum or tympanic membrane and pass the vibration to three small bones, which conduct the waves to the organ of hearing, the cochlea. What can you choose the three little ossicles of the middle ear? What are they called? That was too easy. I should have put hammer. No, wait. Yeah, those aren't on the list for the terms. By the way, we have ears right here. He actually gave them here. So these are the ears that we study from. They hear really well. They're really big. And so this here is the petrous portion of the skull. If you take the bone further in, and that comes off, and then on the inside, that falls out is the tympanic membrane right here. That eardrum that looks like a drum. And then behind the drum, we got these three bones that then vibrate and bring the vibration right to that little thing down here at the bottom, the base. Right here. That little thing. And then that vibrates in there, and it vibrates into the snail. And that's where we then hear. And that little thing is where we hear that. And that's big. That's blown up. And then these rings and this bottom part here help us with balancing, so we don't fall over. Yeah, it's pretty sharp. It's pretty sharp the way that's made. Oh, where was I? Somewhere here, huh? He's cried already. See, there we go. There we go. There's the ear canal, the membrane, the bones, the three bones, the smallest bones in the body actually. And then we have the cochlea here, that's where we hear, and that's where we balance. That's the inner ear. The inner ear is basically a fluid-filled channel system that's carved out of the bone. The snail-looking cochlea makes electrical impulsive sound waves. The three half circles, the semicircular canals, at their base, called the vestibule, and called for starting and stopping motions in different directions, which help us with balance. Within the bony channels, we find membranous channels that are filled with a different fluid. In the cochlea, the bony labyrinth, they call it, together with that membranous one, create three channels together, one on top, one on the bottom, and one in the middle. What are the three channels in the cochlea called? Okay, and which one's this one? Not the Scala OIV? Who could come up with these names, you know? And when you take this model apart, you see little channels in there. So inside those brown things, there is a membranous labyrinth that then inside there's little hairs, and when they vibrate, we hear. That's the whole thing. And so
Those little brown things, what you call them?
the channels.
Channels, okay.
Well, if you look at here, you see here you have the snail here, and then you cut it in half, or you slice it, and then you see the three channels. So you have, this is the bony one, And then in there you got this membrane one right here. So that's the vestibuli, the tympani, and you don't need to know which one is which. I mean, it's not on the list anyway. It's just, and then the vestibule, the media where we hear, and that's the place where we actually do the hearing. And so the next question there, I believe, is going to be the middle of the three channels houses the organ of corti, or the organ that makes a nerve impulse out of sound wave. Its basic structure consists of a bottom membrane which gives rise to specialized hair cells that have cilia or hair sticking up, touching another membrane. When sound waves, which are pressure waves, travel through that area within the cochlea, those hairs then vibrate and fire a nerve. Thousands of sensory hairs are spread along the entire cochlea. The duct within the cochlea narrows as the circle towards the apex. That's important. We'll look at that. Can you name the place at the apex where the ducts connect? Helicotrema. Very good. That's up here. So as you move around that snake, the snail, the first bottom is wide and thick, and then it gets narrower and narrower and narrower. And so when you look at sound waves, where's the piano? There it is. Okay. When you look at sound waves, they come in and they vibrate all the stuff, and then here they vibrate here, and then they go inside that channel. And first it's thick, so the bigger waves, they might hit the wall up here. And as soon as they hit the bony wall, they're going to push down further because they're long waves, and they're going to go through that middle layer, and wherever they cross over, they vibrate that membrane, and the membrane looks like that. So there's a basement, and there's hair sticking out, these cilia, and on top you got some membrane that sits on top. And just sits there and holds these hairs in check. And when we get to the place where those sound waves hit the bony wall and they want to cross over, they're going to vibrate through that membrane. And that vibrates those hairs. And when those hairs bend, the nerve fires. And that's basically it. And now the next question is just basically, where the heck do those waves cross over? And the base, the bottom is wider, and the apex is narrower, so that the sound waves that have a higher wave will cross over where it's wider. They don't even reach up to the narrower area, and the ones on top, they're very shallow waves, so there's a deeper sound. So the higher pitch sounds go over at the base, and the lower pitch sound go over at the apex. That's pretty cool, right? And does that make sense the way I explain it? And then, you know, you put all the complicated words on top of it afterwards, but that's all right. So what was that then?
That was
High pitch, so that's bass, huh? And the part of the inner ear that helps us, so that was the hearing part. All right, and then we go to the balance part. So we have a balancing portion there. It picks up motion, our head does, and translates it into nerve impulse. Any motion starts and stops, even very tiny ones, the head accelerates. And then decelerates. So accelerate means we're speeding up, and decelerates we're slowing down. So we can do that in multiple different motions. We have 5 areas in here to pick up. 2 deal with the up and down motion as well as sideways. You feel those go in the elevator, it goes up real fast and then slows down. Or in the car or the airplane, it goes forward and then it stops as it comes down, or the car stops. The other 3 then encode rotational moments in the 3 planes. You feel those when you spin in a circle or do a cartwheel. You know, that's the one like you spin in a circle and you're good, and then you stop and everything else spins.
Like a cartwheel for us?
Not anymore, my hand hurts. Dude, you know, if I'm in a bad mood, I'd probably do it. I should practice those moves. And the organ of equilibrium, hair cells don't bend to the sound waves displacing them. They bend because they are held in place by a weighted membrane that lags behind, so to speak, when our heads move. So you got these hairs sticking up in these places, and the membrane is on top of it, And so when the body moves, the membrane is a little heavy, they lags behind. So that bends those hairs. And when the hairs bend, then the nerve fires. So that's basically how that works. See, that's how that works. So you got these rocks, these otoliths on top of these membranes, these hairs, and they lags behind in terms of what motion we do. And so two of those will code for forward and back, forward motion, horizontal motion, and vertical motion, and then the other three are the spinning around motions, the cartwheel motions. Probably answered the question, right? What part of the organ registers horizontal movement?
So the utricle tract.
The utricle?
Utricle.
Is that accurate?
That's
Good.
it, that's how you pronounce
Utricle. Yeah, the stuff is too small to label it, so that's why it's not on the list. And so then that's basically what the hearing is, more or less. So we're talking about hairs that bend, that fire a nerve, and then you just do the details. And then what leaves us with that is the taste and the smell. They help us appreciate the world of odors. You know how much you like smell when you have a stuffed nose. Nothing tastes like nothing. 80% of taste is smell. The mouth, especially the tongue and the upper nose, have receptors that detect chemicals. Tiny cilia again, those hairs. They don't sense sound waves, but here they detect chemicals that attach to receptors in the membrane. Our sense of smell is limited as compared to other animals, but even though we pick up thousands of different fragrances and combinations of such. Our mouth, however, only responds to 5 basic tastes. Can you name them?
everything but creamy and spicy.
There you go. Umami, creamy, no,
Not creamy.
not creamy, not spicy, not salty. Oh, that's it.
Yeah.
No, it is salty.
Yeah, just creamy and spicy.
Yeah, just creamy and spicy. All right, well, that's it. Let me make sure we got that. Everything else is basically complicated words put into the situation. All right, so with that, you got any questions?